Okay, welcome to the 9th lecture, and you recall we were gradually going towards a practical transformer, and in my last class this was this slide where this is a practical transformer. Here there is no XM connected, you must understand that it is a practical transformer in the laboratory, okay, 2 secondary, 2 primary, there was nothing like XM connected there. But it was our thought process which led us to believe that okay, this whatever is happening to a practical transformer, what is happening with S open, current drawn from the supply is finite, magnetizing current I m, and when S closed it must be I m plus I 2 dashed, because net MMF in the circuit has to be N 1 into I m. Why? Because flux in the core is decided by supply voltage and frequency. Nobody has any say on that. But if you are trying to disturb the secondary, I mean if you are trying to pass some current through the secondary, primary cannot be a mere spectator to this happening. It will react immediately by drawing an extra current I 2 dashed, and that I 2 dashed cannot be of any magnitude, it has to be I 2 by A. So, that N 1 I 2 dashed becomes equal to N 1 I 2 dashed becomes equal to N 2 I 2. So, that net MMF once again is N 1 I m, and this is what we have discussed last class. So, this is a reactance, this is an ideal transformer and it correctly models it. So, V 1 I m I have drawn. Then I am completing the phasor diagram once again, and suppose this is V 1, to the ideal transformer applied voltage is V 1. So, this is E 1, this is E 2 and this is V 2, V 2, E 2 etcetera, they are all same. So, depending upon the turns ratios your so this V 1 is nothing but E 1, that still remains, nothing in between, and your this will be your V 2 which is same as E 2, and this is suppose the load power factor decides what is the current here I 2, then current drawn from the primary will be I 2 dashed, I 2 you have got, get I 2 dashed, and then this I 2 dashed plus this I m, if you add you will get primary current I 1. Understood? This is how magnetizing current can be taken into account of a, it is somewhat a practical transformer, still not a full practical transformer. I have neglected so many other things till now, only magnetizing current I have incorporated, and for that an external element JXM is to be selected. If you like, you put JXM 1 side 1, okay, because we have seen parameter value changes from side this side to that side and so on. Therefore, what will be the equivalent circuit looking from the primary side? It will be V 1, here is a reactance, no windings this one JXM, and here will be the impedance S square Z 2, is not, this will be the equivalent circuit referred to the primary side JXM 1. So, whatever impedance, voltage, this that are there, and this current I will show as I 2 dashed reflected current, and this current I will show as magnetizing current, and this current is your I 1. Mind you, I am not drawing, but these are dots, that is very important with respect to this. So, this is the equivalent circuit referred to the primary side. What will be the equivalent circuit? Refer to the secondary side, refer to source side, refer to primary or source side, primary side, and refer to load side or secondary side. It will be secondary voltage remains secondary voltage. This will be Z2, secondary things I should not disturb, they are already there Z2. This voltage is V2, this current is I2, I will show it. And this fellow, the transfer of impedance from this to that side will be x m 1 dashed. What is x m 1 dashed? It will be x m 1 by a square. And what is this V 2? V 1 by A. So, this is the equivalent circuit referred to the secondary side. So, you solve this, this you write I m dashed, who bothers, reflected current, and then you will, what current you will get? I will get I 1 dashed. So, you either solve this circuit, get everything, because if this is somewhat practical transformer, solve this circuit, get I 2 dash and then predict what will be I 2. So, people always prefer to work on a equivalent circuit instead of drawing some coupled coils, then individually calculate it. We can do that, but this is a better way of doing things. Okay. After I have done this, our next reality which is present in a practical transformer is let us assume, I will assume winding resistance. Till now I have neglected winding resistances. Are not 0, that is R 1 is present, R 2 is present. That is the, what is R 1? This winding, one side 1 resistance, and this winding has also got R 2, because resistance is after all rho L by A. So, there is some resistivity of this conducting material, some cross sectional area, so many turns are there, so many lengths. Of course, the resistance will be pretty small, it is made of very good material, for example, copper, but nonetheless there will be some finite resistances of primary side and secondary side. And it looks like this resistance which is of course distributed can be considered to be lumped, and I can show it like this. Similarly, for this coil, this resistance I will consider it to be lumped and represent it like this. This is how I can represent. Okay. Now, the question is how this R 1 R 2 should be shown in this transformer. In this transformer, there was finite magnetizing current, no resistance, no leakage flux, fine, and this is I m, magnetizing current taken care of by an X m. So, now once again I will add some parameters to this circuit, that is R 1 R 2 in appropriate place, that is very important, so that effect of R 1 and R 2 will be addressed by this model. Question is, where should I put R 1? Should I put it here? Should I put it there? Where? That is an interesting question. The this portion is ideal, mind you. Therefore, if there is winding resistance, what it is going to do? There will be, whenever this coil will carry current, your practical transformer, there will be a voltage drop here in the resistance. Applied voltage minus this drop is going to create flux. Not this full voltage is going to produce your magnetizing current, because a portion of the voltage will be dropped in R 1. Got the point? Therefore, in this circuit, I will spoil this circuit, do not mind. What I will do now, if I add something here, our previous thing will also get disturbed. So, what I am telling is this, what I will do now, listen carefully. Here I will draw the ideal transformer. And I will put a dotted box around it in order to indicate that, and then these are the terminals of the ideal transformer. Okay. And then I am telling, to this ideal transformer, this winding is not purely this thing. So, your there will be resistances in series. I will connect it here, which is small resistance nonetheless, R 1, it will come in series. Now, the question is, should I put that magnetizing current branch X m before this or after this? I must put it after this. J X m. Similarly, here of course, there is no magnetizing branch, R 2 simply comes here. I have shown only one way, I am showing not like this resistance, because these resistances are small, it only indicates that okay, small resistance in series. Therefore, you know this is the thing, and here is your supply voltage. Frequency f. So, whatever current it supplies, which is decided by maybe the load connected here, ultimately some current is drawn, and when that current flows through the winding, there will be a voltage drop R 1, and that voltage drop must be subtracted from your supply voltage, and the remaining voltage is responsible for creating flux and giving you the transformer action. So, that is why R 1 should not be shown here, it must be after this. Therefore, this is V 1, this is ideal transformer, this is R 2. Now, the moment R 1 is present, I must also distinguish between E 1 and V 1, there will be a drop here in series. X m, what do you think? Its value will be low or high? Its value will be high. You should not choose a magnetic material which requires very large magnetizing current. See, X m is what? X m is approximately V 1 by I m. I should not choose a magnetic material which requires very high value of magnetizing current, then X m will be low. better and better material I use, which is not certainly ideal with mu r tending to infinity, maybe mu r is equal to 5000, quite a large number. So, I m will be small, B 1 is fixed. So, x m is general high, that is why I have written capital letter and with so many turns, just to indicate that okay, R 1 is small, small. Therefore, the magnetizing current which will be flowing here I m is not V 1 by x m, V 1 minus this drop divided by x m. Okay. And as you know, depending upon the degree of loading, the magnitude of the current drawn from the supply will change. Therefore, drop in this resistance V 1 minus this drop is the voltage what is coming here across the ideal transformer. Therefore, the magnitude of the voltage applied to this ideal transformer is will also will not remain constant, as we were thinking in case of ideal transformer apply V. I was telling the level of flux phi max is equal to applied voltage in an ideal transformer is equal to root 2 pi f into n 1, and if applied voltage and frequency is constant, phi max gets decided. But now I come to know okay, the applied voltage to this ideal transformer strictly speaking will not remain constant because of the presence of R 1. This is constant, mind you, V 1 is constant, no doubts, but V 1 minus this drop is what is applied here. What is this drop? This drop depend on the magnitude of I 1 this your practical transformer is carrying, and the magnitude of I 1 has I 2 dash plus I m. I 2 dash depend on I 2 and depend on Z 2. So, by as you change Z 2, I 2 is going to change, I 2 dash is going to change. Therefore, I 1 is also going to change. Therefore, drop in R 1 is not constant as you change loading. Therefore, applied voltage to this ideal primary winding of this ideal transformer strictly speaking is not constant. Only consolation is this R 1 is quite small. Therefore, what people say is this, okay, phi max will be approximately constant, because you have not certainly designed a transformer with high value of R 1 and R 2, then no one is going to buy your transformer. I mean, why? There will be unnecessary power loss in the windings. Therefore, you must see that very good material is used, for example, copper whose resistivity is very low. So, rho L by A the winding resistances are small. So, that way this assumption that phi max practically remains same from no load to full load is good enough. Anyway, nonetheless, let us see try to draw the phasor diagram of this one and try to understand the implication of this. Now, what I will be doing here, listen carefully. Here I will start with E 1 and E 2, okay, this voltage and this voltage. Mind you, here is now that V 2 and E 2 will not be same, is not. Similarly, V 1 and E 1 will not be same, because in between these two sources some I 1 R 1 drop here, some I 2 R 2 drop here will come, they cannot be same. But nonetheless, we can do these things. Suppose how to start the phasor diagram drawing, I will do it like this. Suppose I draw it will be slightly clumsy, but let it be, but follow my argument. Okay, you draw V 2 first, whatever it will be. I draw V 2 arbitrarily vertically. If I know V 2, then I can fix up where the I 2 will be, is not? Because load power factor angle is known. Suppose power factor angle of the load is theta 2, B 2 I 2 I have drawn with S closed. Then I will say, look here, your E 2 is equal to V 2 plus I 2 R 2. Follow the logic. The diagrams may be a bit clumsy, but this is what is going to happen. Suppose V 2 is known, B 2 I 2 you draw. Then I have to add to V 2 this I 2 R 2 drop. Then I will add it. What is there? And I 2 R 2 drop will be very small, because R 2 is small, I 2 R 2. Follow the logic, that is all. If you do that, then what I am telling, you will get your E 2, the induced voltage in this ideal transformer, which I will draw by a red line here. This will be your E 1, E 2, sorry. It is an ideal transformer, this is E 2, then you can confidently draw your E 1. If number of turns of this side is higher, then length of E 1 will be higher than E 2. E 1 is drawn. So, this will be your E 1, and if this is E 1, this is E 2, your magnetizing current will be perpendicular to E 1 90 degree lagging. Here is your finite magnetizing current I m, is not? I have got E 1. So, E 1 by j x m I m I get. So, this is the magnetizing current, and it is an ideal transformer with S opened. I 2 was 0, this current was 0, with S closed, I 2 dash will appear here, nowhere else. It is an ideal transformer, this portion. So, I 2 is known, and I 2 dashed will be in same phase with that. So, I will get I 2 dashed. Whether its length will be higher than I 2 or not, that depends upon the ratios. Okay. So, this will be your it will be less. So, what I will do is I will make this as I 2. So, that this is I 2, and suppose please note these changes, and this is I 1 I 2 dashed, because I have shown E 1 is higher. So, reflected current must be lower I 2 dashed. So, this is your I 2 dashed. Then I will say that this current I 1 will be I 2 dashed plus I m. So, I m is known, I 2 dashed is known. So, I will add these two. Mind you, I have shown I m slightly higher length, it is not so, I m is small, anyway whatever I have drawn. So, this will be your I 1, and if this is I 1, then I will say your V 1 must be equal to E 1 plus I 1 R 1. So, E 1 is known, to this add I 1 R 1 parallel to this, and from this to this, then wherever you will land up, that will be your V 1. I think you have got the idea. See, life will not be so much complicated as we proceed, but what I am telling, this is exactly what how to draw phasor diagram. Start with, I could start with V 1, but it is better you, because the primary current drawn decided by load, it is much more easier. So, I will quickly go through these steps, so that you can understand. Suppose switch is closed. Okay. I will clean this and once again redraw. So, I will just I will, but the idea is very important, you must keep this in mind. Okay. So, I am redrawing once again very quickly. What I am telling, okay, you have closed this switch, this circuit is operating, choose V 2, you start with V 2, okay. Voltage applied across the load is V 2. Then no one can contest me, then the current is I 2 is V 2 by Z 2, and I 2, suppose lagging power factor load, I 2 will lag here, I 2 will be higher, na? Low voltage side I assumed, I mean while drawing. Okay. So, I 2. The moment you know I 2, you can find out E 2, because E 2 is V 2, this drop is this plus minus. So, V 2 plus I 2 R 2. So, V 2 plus I 2 R 2 you draw. These lengths are small, and then you get this length to be E 1. I am simply repeating, because for the first time you are doing this, you get E 1, E 2 sorry. If you get E 2, this ratio of voltage is N 1 by N 2, absolutely no doubt. Mind you, this V 1 by V 2 may not be N 1 by N 2 strictly speaking, but these induced voltages are N 1. So, E 2 is this, then I know E 2 and E 1 are in phase. So, I can get E 1, assuming N 1 is greater than N 2, it will be this. Then once I know I 1, I know the magnetizing current, which will be 90° lagging, and this current is small. Let me draw it now correctly, I m, small current, I m, and once I know I m and I 2 is known. So, I 2 dashed will be this one, here will be your I 2 dashed. So, current drawn from the source will be this plus this is your I 1, and if this is I 1, use this one E 1 plus I 1 R 1, whatever it is parallel to this I 1 R 1, and you get your V 1. Anyway, I am stopping now, but try to understand. So, this will now truly represent, it is somewhat practical circuit with a finite magnetizing current and winding resistance. In the next class, we will bring other realities into an ideal transformer to get a somewhat better picture of the model. Thank you.